Okay, kind of a long story, you don't need to know, but I am running on not a whole lot of sleep because I frittered away my yesterday and then I was up till like 1:30 working on school stuff, so my own fault. So we're going to go ahead, and there's a good chance we'll get through this part. So let's see. I love this topic. The topic of entropy and disorder mean the same, are talking kind of about the same thing. So, and kind of get a running start, we've already talked about these terms before. I'm going to use a beaker to kind of demonstrate. Okay, so let's just say we have a beaker, we'll put a watch glass over it, we have some sort of liquid, there might even be some sort of gas phase. But as I've drawn it, can you see where my system is what's inside the beaker? System, and then my surroundings are outside the beaker, okay? And then, of course, surroundings plus the system is equal to the universe. Okay, so that's kind of how that works. So this is kind of fun. So Mother Nature has certain laws that she operates under. And just a very general law is this, that she will tend to, if possible, hey Quade, she will tend to, if possible, disperse her energy. Now, to me, when I think of that, do you think endothermic or exothermic? Dispersing energy. I'm thinking exothermic, dispersion of energy, exactly. So she just tends to do that if she has a chance. And the other thing that she disperses is matter. Okay, and to me the dispersion of matter is even funner than an exothermic reaction. The dispersion of matter is, and it can be as simple as, if I were to take this piece of paper, and I don't have time to do it right now, but to shred it up into little pieces, okay? And then I can disperse the matter. Okay, that's kind of what we mean by dispersion of matter. Okay, Mother Nature wants to do those things. We're going to be talking about something called spontaneity. Spontaneity. And it's like, if you know somebody's spontaneous, they're like, oh, they can just, just kind of, they're spontaneous. Without even thinking, they do what they do. Okay? So when I said Mother Nature likes to disperse her or his energy, and Mother Nature likes to disperse his or her matter, that's what he or she likes to just do, okay? And spontaneity is something that somebody just does. So what this says is that you can have a physical or chemical process, and it will be spontaneous if it has both of these. My gosh, if you have something that's going on, it's dispersing its energy, dispersing its matter, man, it's spontaneous. What does spontaneous mean? It's just gonna happen. Okay, spontaneity of a chemical reaction. Is it gonna go from left to right? Is it just gonna happen? Now, if you have something that's dispersing energy but becoming what we call more ordered, then we'll have to see. It depends on whether, and if you have something that's taking in energy but it's dispersing its matter, we'll just kind of have to see which one wins out, whether it will be spontaneous or not. We'll be talking more about that. So we talked about state functions before. State functions, it doesn't depend upon the path. We talked a lot about state functions. Enthalpy is a state function. And what we're going to see is that entropy is also a state function. Entropy, I think of, I don't know why, but is it Goldfinger? No. And he has this he talks like that. He's the evil bald guy.
Dr. Evil.
Dr. Evil, yeah. So I think of him when I think of, what show is that from?
Austin Powers.
There you go. I don't know why. What? Very good. So when we talk about entropy, it's going to have the letter S. Entropy, that means entropy. We're talking about how disordered, how ordered a system is. It's kind of hard to put your finger on it because you're like, well, it's spread apart. Okay, that means it's disordered, or it's together. That means it's ordered. We're going to actually put numbers with that, entropy. So entropy is related to the distribution of, I think, matter at the small level, or could be even a large level. To me, I think of my house is a good place for, has very high entropy. Which, high entropy means disorder. Low entropy means it's ordered. So disorder, chaos, randomness, that's entropy. So if you have high entropy, then you have high chaos, high disorder, okay, high randomness. So like I said, the symbol we're going to use for entropy is the letter S. So S means entropy. And entropy will be in units of energy per mole Kelvin. It says if it's for a specific entropy, or if it's absolute entropy, total entropy, it'll just be energy per Kelvin. Whoa. So, changes in entropy track with two quantities. You remember, gosh, it seems like just the other day in Chem 1 we talked about heat and temperature are not synonymous. Heat is thermal energy, and temperature is just temperature. It's like temperature is an indication of the kinetic energy of the matter. So heat and temperature are related to change in entropy this way. Of course, we okay with the triangle. What does the triangle mean? Delta, change in, yep, delta S, change in entropy, exactly. Q is the change in thermal energy. Q is the change in thermal energy. That actually comes from Q is equal to MC sub P delta T. Like, oh, no, not Chem 1. Q is equal to MC sub P delta T. Okay? So, and that's the change in thermal energy. So the change in thermal energy divided by the temperature over at which that change is occurring.
So it would just be in C sub P.
Well, these T's don't cancel. So I think this might be an average. So, and maybe this isn't, we use the change in thermal energy, kind of the calorimetry approach, where we had a certain mass, knew the specific heat, and track the change in temperature to get a change in thermal energy. There are different ways of tracking changes in thermal energy. So, but yes, you're definitely on the right track. So now I have some little paragraphs to kind of think you through what does entropy look like? What does order or disorder look like? And I have some pictures to kind of show what this is. But if you picture a gas and picture a liquid and picture what those particles are doing, which one is more random?
Yes.
The gas. It has more entropy. Liquid has less entropy, exactly. Well, what about a solid? How does that relate to gas and liquid? Does that have more or less entropy?
Or more.
How many people think it has less?
I do.
Yep.
Because the higher the entropy, the more
Yep, the more the chaos. Yep, so it becomes more organized, exactly, it's a solid, just in general. Yep. Yep. This says that the more complicated it gets, then I kind of think the more potential it has for being chaotic. So assuming that the compounds are related, the larger one will have more entropy than the smaller one. This is, oh, go ahead.
Sorry. So for like CH3COOH, we'll have a larger capacity for entropy than like CH3COO because that extra hydrogen made it larger.
Sort of, yeah.
Does that make sense?
Yeah, it does. And I think you picked a good example. You have to be careful that you're kind of comparing apples to apples. So kind of along those lines, what if you would to insert another methyl group, like, or CH2? So CH3, CH2, COOH versus CH3, COOH. So we just inserted a CH2.
Yeah.
This one would have a higher entropy than this one. But you're kind of, I don't know about kicking off the proton. I don't know if that does something else, because you kind of have an acid and a base, basically, conjugate acid-base pair
Yeah.
there.
Okay.
But you're on the right track. So this is kind of fun, kind of reining in the particles. What if you take, it says a pure solid you can have a solute that's a solid or a liquid, and you dissolve it in a liquid solvent. Okay, and in this case, it's becoming more organized. Okay, so entropy. Wait a minute. Oh, it's becoming more disorganized when you have your final answer. Entropy of the system when you make your solution with your solute and your solvent increases. That kind of makes sense because here it's more organized. You go ahead and dissolve a solid into your liquid and it's disorganized.
So it's just like adding more stuff kind of makes it a little like less organized. And
Yeah. Adding more stuff, it's more chaotic. Yeah. Entropy increases. Let's see. Entropy of the system decreases. Why would this be? Why if your solute is a gas? What do you think?
Because it's going from a higher state of entropy to a lower state.
Yeah, the gas itself has high entropy, and you go ahead and settle it down like in your carbonated beverages. And it's like, okay, dude, gas, you can no longer buzz all around. You're right there. You're organized. Yeah. So in this case, entropy decreases. Yep. As the attraction between ions and ionic solid decreases, entropy increases. So take your sodium chloride crystalline lattice structure. Okay, between those Na pluses and the Cl minuses, there is an ionic chemical bond. Different strengths of ionic chemical bonds. So the weaker the bond, the more the entropy. I buy that. I'm trying to convince myself as I convince you guys. So here's some pictures to go along with that. The top one is the first one we talked about, where entropy actually increases. And you can see, of course, S means entropy in the subscript here. So, oh no, this isn't what, we didn't talk about this one. We talked about this right here. We talked about taking a solute, assuming it's not a gas, a solid or a liquid, and dissolving a liquid solvent, and then entropy increases. So it's showing you that by the entropy of the solution is greater than the entropy of the solute and the solvent put together. It's like you said, mixing it up. Up there at the top was that, we actually talked about that one too. You guys told me in solid phase it has the lowest amount of entropy, and its gaseous phase it has the highest amount of entropy. And that's exactly what that's saying. Okay, and this actually gets back to what Mike was saying. If you the more complex you get, the higher the entropy. So, do you guys remember what that little knot means back in Chem 1? Little superscript, like H knot.
Initial?
What? Yeah, it's what?
Initial?
Nope. That would be a 0 down here. Standard conditions. Thank you though for coming up with something. So it means standard conditions, and for thermodynamic problems, you remember what that is? What's that?
25 degrees Celsius.
25 degrees Celsius. Very good. And what's the pressure?
1 atmosphere.
1 atmosphere. Yep. So T is equal to 25 degrees Celsius, and P is equal to, or is it? Well, it's. I think it's 1 bar, so it's close to 1 atmosphere. Well, 1 atmosphere is for gases. All right. So yeah. So you can look at the entropy associated with this big guy versus the entropy associated with this little guy. Higher entropy. Laws of thermodynamics. There are 4 of them. You know, this starts out with the 0th law. You're like, I wonder if they came up with 1, 2, and 3, and they wanted to add once. They went back to the 0th law. I don't know. This one is, to me, it's like a math thing. Like it's the associative property. It basically says if 2 bodies are in equilibrium with a 3rd body, then they are in also equilibrium with each other. Thermal equilibrium. Like, well, no, duh. So, I know that's, to me, kind of strange.
So is that kind of like A equals B and B equals C, so A minus B?
All right. Definitely. Yep, exactly. Okay. Internal energy of a system. Okay. So, I'm going to go ahead and draw my beaker here. My beaker is the system, remember? And outside is the surroundings. We're going to be talking more about this. So this says that the energy of this which is the system, okay, will increase as you transfer energy from the surroundings into the system. So E in. Makes sense to me. So you can do it that way, or, and we're going to talk about this after your test next week, you can add energy or you can perform work. Work on. Energy in or work on. Beat it up. Okay, make it smaller. That's performing work on it. Or you literally add energy. And in both of those cases, the energy of your system will increase as it's been worked on by the surroundings or got energy from the surroundings. To me, it's just a picture thing. This one's cool. So this is like an astronomy thing almost, like the universe. Now you can think of universe like this, or like outside your beaker, or you can think of universe like as in the galaxies are contained within our universe. The total entropy, that's S, of the universe always increases. But that's assuming that the processes going on are spontaneous. So for spontaneously occurring processes, the entropy of the universe will be increasing. Entropy increasing, becoming more disordered. Now, I'm not sure this is really what it was meant to be, but like if you have a neighborhood that you visit, you know, and think of yourself visiting it over the years, like, and think of somebody like a house that's neglected. And think of the paint job a house undergoes over the course of 10 years. Okay? On the small scale, it's becoming more and more and more chaotic. Entropy is setting in. The matter is dispersing. Okay? That's how I think of that.
So because the matter on that house is dispersing, the entropy for the entire neighborhood will increase? That's kind of what you're saying, like it will lead to the...
Entropy, so if we call the house the system, and it's increasing,
I get what you're
then the
saying.
universe, the overall, that system is housed in the universe, so the universe
Yeah, okay.
is, yeah, I think so. Because, yeah, that makes sense, because the universe is the system plus the surroundings.
Yeah, so just be adding that to...
Mm-hmm, yep, yep. That's neat. The last one, and we'll be using this actually when we work problems with entropy. Now, think of what this says though, absolute zero. When you think of the word absolute zero, what do you think? 0 Kelvin. And would you want to be at 0 Kelvin?
No.
Well, Quaid would go with
Might be
it.
the first one, so, you know,
Human popsicle.
yeah,
So what happens at 0 Kelvin to matter?
stops.
Stops moving, yeah. So all motion stops moving. And so this says, now you have to, the matter has to be in its pure crystalline solid state, but if you can get anything to cool down to absolute zero, then its entropy is zero. So think about it. Maybe we don't use that in problems. I think we use something else in problems, because I don't think we work problems at absolute zero. So, what's that?
We're gonna do it.
So, S is entropy, and so as we were saying, Mike was saying, so the change in entropy of the universe is the change in entropy of the system plus the change in entropy of the surroundings. Now, go back to your house, okay? Spontaneously, the house is going to go to matters disordered. But we could put a little bit of energy in that, go over and sweep up the crap that came off the house, organize things, okay? Now, that's not spontaneous, though, right? That actually took a little bit of effort.
But
So,
that would be putting work on the system, but would technically lower the entropy, wouldn't
that would be performing work, which would have and in addition to performing work, the outcome of that particular work would be, decreasing the entropy. Yeah.
it? But the first law says that anytime you put work on it, it increases entropy, right?
When you put work on it, increases not the entropy, increases the energy.
Oh, okay.
Yeah, energy. Yeah, this first law. Yeah, internal energy increases. Yep. That's so cool. Okay. All right. So Does this look, remember these delta, these, are the summation of? Do you guys remember the summation ofs? Okay.
It's been a while.
Yeah, we'll do a problem to kind of remind you. But, and one of the things, whenever you see a delta, it's always final minus initial, and that's exactly what you're seeing here. The change in entropy of the system is the summation of what the entropies are in their final state minus what the entropies were in their initial state. So that's the change in entropy. But that's probably not the form you're going to use it. This is the form you're probably going to use it. Where, I'll just put this whole thing up here. This to me is very similar to your one way to calculate change in enthalpy. Now, does that not drive you nuts too? Entropy and enthalpy? I hate it. Well, okay, it doesn't drive Livy nuts, so that's good. But they start with letter E. Entropy and enthalpy.
No, I said it kind of did.
Oh, it does kind of? Yeah.
Yeah, because they're like close.
They're similar. It's like direct. So when we did change in enthalpy before, we said the delta H of the reaction is equal to what? The products, change in entropy, enthalpy of the products minus the change in enthalpy of the reactants. And that's kind of what we're doing here. We're going to do the summation of, and the little a and the little b, those are stoichiometric coefficients. Those are stoichiometric coefficients. Okay? So let's just do one, see what it looks like. So it's always final minus initial, products minus reactants. Oh, here we go. Yeah, and this was what we were talking about, the little knot means. So the thermodynamic standard conditions, like Quaid said, it's 25 Celsius and 1 bar. And then if you want to kind of make a mental note, because we're going to get to this point where the other thing you need to know about this little knot, that means if it is an aqueous solution, that the molarity is 1 molar. Seems kind of concentrated, doesn't it? That's the other standard. That's the third thing that is important. All right, so now let's do a problem. So to work this problem, we're going to need these standard molar enthalpies. Do you see why we call these standard molar enthalpies? Because they're the enthalpy per mole. Okay? You can see that in the heading. All right. So let's work this problem. This is just the combustion of methane. Methane gas reacting with oxygen in the presence of flame to form carbon dioxide and water. So here we go. So we're supposed to knock out the change in entropy using that table that we just looked at. And then we're also supposed to, once we come up with the change in entropy, we're going to say, is this system becoming more ordered or more disordered? The thing is, if it's a positive delta S, that means it's becoming more increasing entropy. So it's becoming more disordered. If it's a negative delta S, that means it's becoming more ordered. Okay? All right. So these are the values that I'm pretty sure that they were on the previous table. So I basically just kind of picked these off of that table. So these, again, are kind of, when you worked your enthalpy problems, you had to have the standard molar enthalpy. These are the standard molar entropies. Yes. And if this happens to be, remember you're going to have a few of Unit 5 questions on your final. If this is the question on your final, you have to show all of your work. Okay, so remember how that works. So I like to kind of divide it into, I work my summation of my products, and then I work my summation of my reactants, and then I do one last subtraction. That's how I do it. So the product side looks like this, where we have 1 mole of CO2, the standard molar entropy is 213.7 joules per mole Kelvin. The stoichiometric coefficient associated with the water on the product side was 2. So we have 2 moles of H2O. and its standard molar entropy, entropy, that'll do it. So enthalpy or entropy. Entropy is 69.9 joules per mole Kelvin. And that's it. I need to go ahead and do my math and summarize it. And you'll come up with, on the product side, 353.5 joules per Kelvin. So I know we got a little janky with the equilibrium constants where they were unitless, but we're back to counting units. So see how moles cancel? Okay, moles cancel here. All right, so that's the number that we're going to then subtract from that, the summation of the reactants. The reactant side looks like this, where the coefficient in front of the CH4 was 1, so 1 mole of CH4 times its standard molar enthalpy. Entropy, darn it. Standard molar entropy, 186.3 joules per mole Kelvin. And then we had 2 moles of oxygen, so the next term is 2 moles of O2 times 205.1 joules per mole Kelvin. Again, the moles cancel in both of those terms, and we're left with units of joules per Kelvin, and the number is 596.5 joules per Kelvin. So I really like working them this way, because then you can't mess up. You're less likely to mess up. Now we need one more subtraction then. Down at the bottom, I'm going to take the first number and from it subtract the bottom number. So 353.5 minus 596.5 units are joules per Kelvin will give us a negative 243.0 joules per Kelvin. So entropy is decreasing. Yep, entropy is decreasing. So let's see. Yeah. So it's becoming more ordered or disordered? More ordered. Yeah, more ordered. And so you might be like, well, last I saw you could burn methane pretty easy. It looked pretty darn spontaneous to me. Well, burning methane, is it endothermic or exothermic? Exo. Yeah, it makes a lot of heat. So here's where you have the dispersion of energy, but the decrease in entropy, so matter coming together, dispersion energy, matter coming together. Now, in that case, the dispersion of energy kind of trumped the matter coming together, so it is spontaneous. So those two terms, in order to see if it's spontaneous or not, we'll be doing this. You have to see which one kind of trumps the other. If they're fighting spontaneity, which one wins out? Okay. Yep. So since the change in entropy is negative, then it's creating order. Oops, sorry. Full show. So here are a bunch of tables. I think I skip them. The difference between this table, and I'm going to kind of skip it, is notice that these are inorganic substances. And we'll be talking more, so you see the standard molar enthalpy of formation. The last column is the molar entropy. The middle column is Gibbs free energy of formation. We'll be talking more about that. There's the second. Oh, wow, I thought I skipped all these. Oh, skipped several slides. Okay. There's the end of the inorganic, and then this is the beginning of I only have 2 for organic substances. So these are the organic substances with the same 3. These are all thermodynamic properties of these compounds. And then we get to, dun dun dun, this one. So we said that actually oh goodness, in Gen Chem 1, we said that if their pressure is constant, then actually your change, your Q is equal to your change in enthalpy. But notice now, this is the surroundings and this is the system. Does that make sense? And the difference is they are like opposite of each other. Anyway, okay, so on to these problems. Let's see if this will work. Take a quick look. I didn't look at these before, but they should be here. 19.1. There they are. So these aren't too bad. Come on, sending project. Oh, you want to do it. In order to make this work, I had to bring in my laptop from home. I'm like, really? Are you serious? I don't know what I'm going to do next semester. Anyway, it's coming up. I'll tell you what one looks like. I'll just read it. Oh, there it goes. Nope. Flicked it out. Back at me. It says, basically, kind of like a minute ago, you had to say, is the entropy increasing or decreasing? It's not too bad. You guys will be fine with it. So these will be due on Friday when you come. Wait, yeah. There it goes. Okay, dang. So remember that if we say the entropy is increasing, it's increasing disorder, so it's going to be positive delta S. If order is increasing, disorder decreasing, it's going to be a negative delta S. I think you're fine with that. Okay, the next one looks like this. What's my hint here? I think my hint here is if you have, for instance, kind of from left to right, you're supposed to compare, just eyeball what the entropy might be between those two things. When it gets to, for instance, well, I guess B and C, where you have atmospheres and millimeters of mercury, I think you need to make them into the same units of pressure and go from there. Kind of think through those. And the next one looks like this. Indicate whether entropy of the system would increase or decrease with these reactions. If you can't be certain, by inspecting, explain why. So like, what do you think? The first one. How many people think that that's increasing entropy? Very good. What do I have? Oh, goodness gracious. I'm not sure why you see where it says B? And I like hand wrote that out. So what do you think? How many people think that that looks like it's increasing entropy? Ah, decreasing entropy. You guys are great. So, okay. On to the next one. Explain which one would have the greater entropy. So I kind of have hints there you may or may not need. Okay, it's just kind of more the same. And then this is the last one. So I don't think, I could be wrong, but as I'm looking, I didn't look at these before class just now, but I don't think you need to do the summation and all that stuff, do you? I didn't see that you did. But this one, do you think you need to?
I just
Eyeballing it, yeah, that's what I'm thinking too. Cool. And actually 7, the answer is in the back, you can find under doc sharing. So that's all I have today. Yay.